Welcome to the 7th lesson in this series on Area of Study 3. Today we'll be having a look at special relativity and a little bit of an introduction into the basics of it. So we're going to do a few things. We're going to have a look pretty much what is special relativity, so kind of why it was conceived. We're going to have a look at conflicts using Einstein's Gedandken train. We'll have a look at his postulates as well of special relativity. We'll take a brief look at Galilean physics before we move on to the concept of space-time. We'll contrast a couple of models and then we'll do a little bit of an introduction into the Lorentz Factor. Okay, so special relativity is a theory concocted by Albert Einstein to explain the relationship between space and time, specifically to unify Maxwell's equations and Newtonian mechanics. Now, within this course, you don't do Maxwell's equations specifically. You may have looked at it briefly in 1-2 physics, but aside from that, you don't need to know it. Special relativity is part of a broader topic called general relativity, which is not part of the course either. Electricity and magnetism are related, which was one of the results of unifying these equations. And so now it's known as electromagnetism. So that's kind of special relativity and its impacts. And just so you know, general relativity, very briefly, includes gravity, space-time curvature, and accelerated frames of reference. And special relativity doesn't touch on any of those things. Okay, so this is a bit of a famous scenario, and it's used to explain the concept of simultaneity, and it gives a reason why special relativity is needed to explain phenomena for things traveling at close to light speeds. So it's what we call a thought experiment, which means it's something that you can't really easily do physically, and so you have to kind of imagine it. It gives reason as to why events in one frame of reference may not be simultaneous in another frame of reference. For the observer in the train, the light would appear to reach both ends of the carriage at the same time, because in their frame of reference, because they're all traveling at a constant velocity, and the light globe is attached to that carriage, it looks to them like it travels at speed c in both directions. However, for an external observer, it would hit the back wall first, because the velocity of the carriage would suggest that at speed c, there is less distance to travel going backwards than there is going forwards. That means that, and only because the speed of light is a constant, other parameters must change, like length and time, to explain the difference. So that's why special relativity is required to explain this kind of thing. And this thought experiment specifically is a really good representation of things that should occur at the same time but don't. Okay, so there's Albert Einstein on the right for you. Great bloke, didn't know him, but he looks great. The laws of physics are identical in all inertial frames of reference. And an inertial frame of reference is one where no acceleration is applied, so it's traveling at a constant velocity. So those laws are the same when the object is traveling at low speeds and at high speeds, provided that that object is not accelerating. And that's what we call Einstein's first postulate. I think that in terms of postulate, there are only 2 postulates, but this one is probably the most useful in terms of its applications to special relativity. The second postulate is that the speed of light is the same for all observers, regardless of the motion of the light source or the observer. And this was a finding based on another experiment run by 2 others. And they found that when they were setting up an experiment to see how fast light traveled through the ether, which was what space-time was thought to be, it actually traveled in all directions at the same speed, which wasn't the prediction. So that value of the speed of light in a vacuum is 3.0 times 10 to the 8 meters per second. All right, practice question 1. Giving at least one example, explain Einstein's first and second postulates. 4 marks. It's an explanation question, so it may take you about 4 minutes to write down an answer. So you can pause the video and get back to it once you have finished the question. Okay, now that you've had an opportunity to do that question, let's see how I would answer it. So the first thing I'd note is that Einstein's first postulate indicates that the laws of physics are the same in any inertial frame of reference. So the laws of physics must be the same in a car traveling in a straight line at a constant velocity of 60 kilometers per hour and a spacecraft traveling at a constant 0.2 c, so where c is the speed of light, in a straight line. And what I mean by the laws of physics is I mean that if you were to, I don't know, juggle some balls, they would act in the same way. Einstein's second postulate infers that the speed of light is a constant of c, regardless of the motion of the observer and the source, such that the speed of the beam measured from one spacecraft traveling at 0.6 c towards another spacecraft traveling at 0.5 c in the opposite direction is the same. So it's just saying, well, regardless of the motion, we both observe the speed of light to be c. Now we move on to something that isn't Einstein. So Galileo had some ideas about physics, and his models of motion work at low speeds only. And that's what you've learned in kinematics and motion so far in this course. So all the Newtonian mechanics is derived, combines with Galilean physics, and that stuff works really well. It only works well at low speeds where relativistic speeds aren't reached. And we'll see that a little bit later when we have a look at the Lorentz factor. So as long as the velocity is less than, say, 100th of the speed of light, so that would be about 3 × 10⁶ meters per second, you won't really notice any effects at all in terms of the time or length. So when it's applied to high speeds, and when I talk about high speeds in this course, I mean something that's going at relativistic speeds, it indicates that the objects, given sufficient energy, will be able to exceed the speed of light and continue to increase indefinitely. So that's kind of one reason, one difference, I suppose, which we'll see a little bit later when we're comparing the two models of Galilean physics. So Einstein recognized that flaw and realized that some transformation was required to ensure that a model fit both low and high speeds. And this result is special relativity. Isaac Newton declared that space and time were absolute and unchanging. So in a bit of beef, you could say, Einstein did the opposite. He said that space and time were actually one entity known as space-time, and that this entity was constantly changing. So space would contract and time would dilate. To the right, we see kind of an illustration of space-time, and it's warping under the influence of gravitational fields. So it's a common idea that things that have mass put little, I guess, bumps or divots into the fabric of space-time, you may have heard, and that's kind of one of the things that Einstein was talking about. Experiments show that Einstein is in fact correct with understandings such as those with muons and atomic clocks, which we'll have a look in the next lesson, such that time has been shown to get longer and distance shorter in the frame of reference of the observer. So compare how Einstein's and Newton's understandings, compare their understandings of space-time. Give an example to support your answer. So 3 marks. You can probably do this within 2 or 3 minutes. Pretty straightforward. And you can pause the video and get back to it when you're ready. Okay, now that you've had an opportunity to do this question, let's see how I would do it. So the very first thing to say is that Newton claimed that space and time were absolute and unchanging. We saw that in the previous slide. That would be worth 1 mark, probably one of the easiest marks you can get. So what is it? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 words. On the other hand, Einstein claimed that time would dilate and that space would contract relative to the stationary observer. So what that means is that there's a difference here in space-time. One saying that, well, it's rigid and doesn't change, And Einstein's saying, well, it does change. And the example, which again, pretty much rewording the previous slide, is that experiments with atomic clocks and the observation of muons on Earth's surfaces support Einstein's conclusions. You don't need to add anything else to this. It's only 3 marks, so you should have about 3 valid points. So you'd have 1 mark for each of those dot points. And little caption there, space and time are one entity under Einstein's understanding. Okay, we've got a little bit more of complication now when we introduce the Lorentz factor. So the Lorentz factor expresses a multiple by which the physical properties, so mass, time, length, momentum, etc., change as a result of approaching speed of c. It's the basis for calculations involving special relativity because those involve higher speeds. All right, so we have this equation here. Gamma, this letter here is called gamma, equals 1 on the square root of 1 minus v squared on c squared. And that is the Lorentz factor, that gamma. It doesn't have a unit, as we can see down here, and v is obviously the speed of object, and c is the speed of light. Some important things to note with gamma is that v can be anything as long as it's more than 0, because velocity, it has direction, so we can always express it as a positive quantity with a direction. So that there's no real restriction on v. What is important, though, is that v is less than c. And that must be the case because you can't exceed the speed of light. And so in the end, we get this restriction with 0 is less than or equal to v, which is less than c. That's the only thing that you need to be aware of. So make sure when you put this into your calculator, v is always less than c, because if it is c, then we get an undefined answer, and that would result in some complications and issues when solving the question. In terms of values for gamma, because it's going to be 1 on the square root of 1 minus something, and that something can be between 0 and 1, at most, it can be really, really, really close to 1, which would infer that it's close to infinity. So gamma can go up to positive infinity, but it also can't get less than 1. And the way it can't get less than 1 is because when v is 0, you get 1 on the square root of 1, which is 1. So gamma must be an element, or must be between 1 and infinity. There we go. That's a bit better. Hopefully you should be able to understand the basic mathematics there. A little bit complicated, but I'm sure that you'll be able to cope. All right, so a black spacecraft is traveling at 0.6 c. So 0.6 times the speed of light. Calculate the speed in meters per second and find the Lorentz factor. 2 marks, which should take you probably less than 2 minutes, but you've got up to 2 minutes to do the question. Okay, now that you've had an opportunity to do that question, let's take a look to see how I would approach it. So the first thing I'd find is the velocity, and that's very straightforward. It's 0.6 times by c, so 0.6 is there, and the c is there, and you can pretty easily simplify that to 1.8 times by 10 to the 8 meters per second. The next part is finding the Lorentz factor. And we're going to have to use this formula, as we could see from the previous slide, and substitute in v. So v is going to be 0.6c, which I've put over there, you should be able to see. And simply now just a cancellation of the c squareds, because when you square this out, you can cancel the c squareds on both the top and bottom, the numerator and denominator. So what you get is 1 on the square root of 1 minus 0.6 squared. And that simplifies to 1.25. So that would be our Lorentz factor for that question. Okay, part B, a silver spacecraft has a Lorentz factor of 10.0. Calculate its velocity in terms of the speed of light through a vacuum C. Got 3 marks here. Hopefully it takes you less than 3 minutes, but you've got up to 3 minutes to do the question. You can pause the video and get back to it once you've finished. All right, now that you've had an opportunity to do this question, let's take a look to see how I would approach it. So the first thing I would write down, which is already written down very nicely in that diagram there, is that gamma is 10.0. I would then equate gamma, so using that formula before, to the 1 over square root of 1 minus v squared on c squared. And then quite simply, now it's just an arithmetic solution. So we'll square both sides, and we will also apply the inverse to both of them. So we get 1 on 100 equals to 1 minus v squared on c squared. We can put the 1 over and get rid of the negative, and you get 99 over 100 is v squared on c squared. And then you can, quite straightforward, just solving for v. I would keep the c squared out of everything before you square root it. That way you get the square root of 0.99 multiplied by c, which is 0.995 c meters per second forward. So that's kind of how I would approach that question. In terms of your mark allocation, you probably get 1 mark for doing this, another mark for doing something like that, and another mark at the end. Make sure you include forward or something like that, or in the direction of motion, because it asks for velocity. Velocity is a vector, so you are required to give a direction. All right, that brings to a conclusion this lesson. We had a look at the following things. We had a look at the introduction to special relativity. We had a look at Einstein's 2 postulates. Hopefully you remember. First one, that all laws of physics are the same in inertial frames of reference. And the second one, that the speed of light is a constant, regardless of the motion of the observer or the source. We had a look at Galilean physics and why it doesn't work at high speeds. And we also had a brief look at space-time and how Einstein and Newton interpreted it differently. To finish off, we had a look at the Lorentz factor, which is that gamma equals to 1 on square root of 1 minus b squared on c squared. And in our next lesson, we'll be taking a look at muons, which are subatomic particles, time dilation, and length contraction. So that's a pretty big lesson, really important part of the course. And I would say probably one of the hardest bits to understand. The special relativity is A, special, and B, it's relativity, which means that everything is relative to other stuff. So you've got to understand what you're doing. Thank you very much for your attention during this lesson. Hopefully you found that it was interesting and that you learned something new. If you would like to get in touch, feel free to go to the airlearners.com website, and you can find me on the tutors page. I'm about halfway down somewhere. Thank you very much for your time, and I will see you next time.